Hello students, welcome to this lecture number 7 on the chemical equilibrium chapter. In this lecture we are going to discuss a very important thing regarding the equilibrium constant, that is the application of the equilibrium constant. So heading of this today's video is application of equilibrium constant. So today's video is application of equilibrium constant K. There are basically three applications that you can observe. Number one, that is the prediction of the extent of the reaction. Number two, the prediction of the direction of the reactions. And number three, the calculation, or you can say determination of the concentration of equilibrium mixture at the time of the equilibrium. What will be the concentration of the reactant and product at the time of equilibrium from the initial concentration you have been given. These two first applications we will discuss in this video, and the next lecture we will discuss the determination, how we can able to determine the compositions of the concentrations of the reactant and product. So in this video we are going to discuss the two applications. That is, first we are going to discuss the prediction of extent of reaction. Extent of reaction. Very important thing to understand. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. When we are talking about the extent of reaction, there are basically three categories you can find. Number one, that when all the reactants has been converted into the product, that is the first category. In that time you will find at the end the reaction is almost completed or almost finished. Second category that you will find that at the equilibrium time there will be the appreciable amount of concentration of the reactant and product. This is the second category. Third category, that reaction is hardly proceed, means there is very few reactant have been converted into the product. That is the three categories of the extent of the reaction. Now question arises, how do the equilibrium constant going to help you predict all the things, all the three categories of the extent of reactions? We know what is equilibrium constant. Equilibrium constant is basically a ratio of the concentration of product, and it is divided by your concentration of the reactant. So when we are talking about the extent of reaction, means we are basically talking about the ratio of the concentration of product and the concentration of the reactants. When the concentration of product will be much higher than reactant, we will say the reaction has been completed. When it is 50-50, we will say the reaction has not been completed, but there is a appreciable amount of this. And last one, that reactant not has been converted into the product very much. That is, very less amount of reactant has been converted into the product. So equilibrium constant is basically the ratio. So higher the equilibrium constant. So equilibrium constant, one thing understand, equilibrium constant K is basically the concentration of the product divided by concentration of the reactant. So from this relation you can able to say that equilibrium constant is directly proportional to product and also it is inversely proportional to the reactant. Inversely proportional to the reactant. So what it means? This means that when this value is will be numerical value will be the higher, then it is suggest what it suggests there is a more concentration of the product at the time of equilibrium when the equilibrium constant is very high, and when the equilibrium constant is low, that you can say that is there will be the presence of the reactant as compared to the product. So from this numerical value we can able to say about the extent of the reaction. When the K value is high means the reaction has been on the verge of completion. When it is less means that is reactant is dominant over the product, that the reaction has not been proceed much. So for a general representation, general expression, general understanding, generalization of this extent of reaction, what we can say that there is a thumb rule. Thumb rule is this: if K value is greater than 10 to the power 3, then we will say product is dominant over the reactant. We can say product is dominant over the reactant. Product is dominant over reactant. And if this value is very much high, very much high, then we can say the reaction is completed. We can say reaction is completed because all the reactant has been converted into the product. Let us have some example of this. Suppose first example we are taking that when the hydrogen gas reacted with the oxygen gas, it will going to prepare the H2O gas. So we can write this reaction. This is a reversible reaction, but this reaction has a very high conversion speed. You can see that is its K value, you can see that is 2.1 into 10 to the power 47. So you can see its K value is very high, and that is why this reaction is on the verge of completion. When you see the reaction is almost completed and it will give a K value is very high. It is indicative that at the reaction the product will be dominant, very much dominant over the reactant. Second reaction that we are going to discuss, that is H2 gas. Here you have to put the gas sign, gas, and this is also gas. H2 gas and Cl2 gas. It will produce the HCl gas. Its K value you can see that will be coming around 4.1 into 10 to the power 31. So you can see this reaction also you will find that is the equilibrium time. At the point of equilibrium you will find that the product is dominant over the reactants. So this type of thing that we can understand how the K value is going to say about the extent of the reaction. When the K value is high means there is a higher concentration of the product. If K value is low, there will be the lower concentration of product at the time of equilibrium. Now we see that is when K value is greater than 10 to the power 3, and here another thing that we are going to understand, if the K value is low, with the example, how it will going to give us a information about the extent of reactions. So you can see this is the Kc and this is the 1 point when value of the Kc is 1, when the value of Kc is 10 to the 3 and when this value of Kc minus 10 to the power minus 3, that in this zone you can say that product and product concentration and reactant concentration is appreciable. Reaction concentration is appreciable. Here the Kc value is very high, so you can write the reaction is almost completed. Reaction is almost completed. Reaction is on the verge of completion, and here it is negligible, very low Kc value. So we can write the reaction is hardly proceed. Reaction is hardly proceed. Hardly proceed. Okay. So these three type of things, that how you can able to now understand how equilibrium constant is going to help us predicting that the extent of the reaction. When the K value is very low, below 10 to the 20, below 10 to the power minus 3, then it will have the concentration of the reactant is dominate over the product, or we can say there is a very little amount of product has been produced. But when this value 10 to the minus 3 to 10 to the power 3, we can say product concentration of product and concentration of your reactant is appreciable. When this value is very high, you can say reaction is almost completed. So this is the application of the equilibrium constant regarding the extent of reaction. Now we will be talking about how do we able to predict the direction of the reaction. Now second point, that is a prediction of direction of reaction. Direction of reaction means from the K value we can also able to predict the direction of the reaction, means which direction the reaction is going to proceed, whether it is in the forward direction or in the reverse direction. How? Now for that you have to have a quantity, it is called the reaction quotient. It is called the reaction quotient. Reaction quotient. Reaction quotient is QC for when you are talking about the concentration terms, that is in terms of mole per liter, or it is QP when you are talking about the partial pressure. Two type of reaction quotients we will able to understand. Reaction quotient. So from the reaction quotient, how do we able to calculate the reaction quotient? Reaction quotient has been calculated the same way that we can able to calculate the equilibrium constant. So, but difference is the concentration terms of the partial pressure term, it is not at the equilibrium term, it can be at any time. So for this reaction, this is the reaction. The reaction constant will be the similar way that we calculate the equilibrium constant divided by now what is the relation between the prediction of the reaction, direct prediction or direction of reaction, and this quotient. It is said when QC is less than Kc, means equilibrium constant, then reaction will go in the first forward direction. Reaction goes in the forward direction. Okay. When QC is less than, QC is greater than Kc, then reaction goes on the reverse direction. When QC is equal to Kc, means the reaction has equilibrium. This is the equilibrium point. So now we will going to understand from a practical example how this reaction quotient can be helpful to understand the direction of the reaction, and in the exam there will be questions, numericals like this. Suppose we are taking example of a gaseous reaction. Gaseous reaction is, this is the gaseous reaction. The concentration of hydrogen at any time, at any arbitrary time, it is not necessarily at the equilibrium point, at a time, that is, suppose it is 0.1 mole per liter. Concentration of iodine, suppose it is 0.2 mole per liter, and concentration of HI, suppose at any point of time, it is 0.4, and its equilibrium constant K is given 57 at 700 Kelvin. You have to say at this point, when we calculate, when we measure the concentration, in which direction at this point, whether we are able to predict about the direction of the reaction, whether the reaction goes in the forward direction, whether it is in backward direction, or it is in equilibrium. How can we calculate? For that, you have to calculate the reaction quotient. Reaction quotient we know from this will be this, and here this is the concentration of the whole square divided by 0.1, and this is 0.2, and you will calculate it, it will come around 8. So now you understand, 8 means what? That is less than the equilibrium constant. When it is less than the equilibrium constant, that we understand the 3 guidelines that we have already discussed. When QC is less than Kc, then the reaction will goes on the forward direction. That you can see. So this reaction at this point, when the equilibrium, when the concentration of this reactant and product is this, means the reaction will go on the forward direction. It is not in the equilibrium point, because if the quotient is equal to this K, then it will be at the equilibrium point, but it is in the forward direction. The reaction will go on the forward direction. The H2, I2 will react with each other, and it will going to give the HI. That is how we can able to understand the direction of the reaction. In the exam, in the question, numerical will come that this concentration will be changed, and you have to say from this data what you are able to predict, whether the reaction goes on the forward direction or the backward direction. That will to give this type of numericals that will come. Then we will take another example. This is the reaction, and its Kc value is given here at a given temperature. Suppose at a given temperature, its Kc value is given here, and this is reaction, and the concentration at any point we calculate, we determine the concentration in the experiment, when we found the concentration of this reactant and product itself. Then you have to predict about the direction of the reaction, in which direction the reaction will continue. You can pause the video and you can do with yourself, then you can able to understand the concept very clearly. So what we do for that, we have to calculate the reaction quotient. Reaction quotient QC, that is, you can see the concentration, first the concentration of the product in the numerator and this concentration of the reactant in the denominator. So what we have given? We have given all those constant, reaction constant, it is same. So you can see, and it is, suppose it is 1 molar. Then what will happen? 1 into 1 divided by 1, that is 1. So this means the reaction quotient is here 1 mole. So 1 means here equilibrium constant you are giving 2 into 10 to the minus 3. So what is there? Now KQC, reaction quotient, in this case reaction quotient is greater than, here reaction quotient is greater than the Kc. So when reaction quotient is greater than Kc, means what? Now reaction will on the reverse direction. Okay? So in this case reaction will be on the reverse direction. So you can understand easily that first you have to calculate the reaction quotient, then you have to compare with the equilibrium constant. So from this comparing the equilibrium constant, you can able to understand whether the reaction is proceeding in the forward direction or the reverse direction. So you can make a summary of this, all the predictions of the directions. When QC equal to Kc means that reaction at equilibrium. And that is the third thing. Here QC and Kc. That is, we can say reactant, product to reactant on the reverse direction. So you can summarize this what we have discussed here, that from the QC reaction quotient and from the Kc you can able to, how we can able to predict the direction of the reactions. Okay, that is all for today's video. We have understood what is the application of the equilibrium constant. If you like this video, you can share with your friends. Thank you very much for watching. All the best.